Hi everybody. So today I made a video about the power transfer in electromagnetic fields. So some months ago I was asked a question how actually the power is transferred from a source to a load, and it seems like people struggling a little bit with the concept of using the pointing vector also at DC. And finally, like yesterday, there was another discussion because about a video from YouTube which was pointed on the channel called Veritasium, where they state that the energy doesn't flow in wires, it flows in the space around the wires. And I can really highly recommend Veritasium. It's a very nice channel. They have all different science topics, and the discussion actually went the path that even if we have the pointing vector and the power travels around the wires, there will be of course a skin depth, so the fields will be able to penetrate into the wires. So some people are claiming like that the power is not only flowing outside of the wires but also inside, and this is something I would like to demonstrate today. So I made a very simple setup. It's a 10 centimeter basically ring of conductive material. It's got the conductivity of copper. The thickness is 2 millimeters, and I have a source placed here. This is port 1 and a resistor at port 2. So I'm feeding the source with 1 volt. And let's take a look at the fields and see what's happening. So I hide all the dimensions and we go directly to the field results. I have various frequencies just to make sure that we can visualize the skin depths. So starting at, I have 1 hertz, basically behaves like DC power. Let me switch to an arrow plot, and we are now looking at the electric field, and obviously the electric field will point from the, let's say, from the one arm to the source to the other. That's exactly what we see here. So here is the source. The electric field is pointing from the one half ring to the other half ring, as we would expect. And if we look at the magnetic field, again going back to 1 ohm, obviously the magnetic field will be located around the wire, so we have to choose a different cut plane. This is the cut. Let's not look through the port, but look like at the other half of the let's look at the other half. So yeah, obviously, as you would expect from field theory lessons, the magnetic fields points around. And now if we do the cross product to calculate the pointing vector, we don't need to do this manually. We have a so-called monitor which is called the power flow. So if we look at the power flow, it's now I have to roll it back and go back to this kind of plot. The power obviously flows around the wires from the source to the load, as you would expect it. It's of course not located just around the wires. It's not a, fields are in all of the regions, so it's not like a binary thing where the power is only around the wire. It will distribute in the region, it will even flow from here to there, but obviously the highest portion of the power flow will be located around the wires. If you see, this is still red, this is still red. So this is as shown by Veritasium. It's clear that it needs to behave like this. But now what about the skin depths? What's happening there? So if we look at the current, so this is now the current density inside the conductor. Let's start with the current because that's the I think a little bit the most obvious thing. If we look at the current which is distributed in the wire, obviously at 1 hertz, it's pretty much evenly distributed over the wire itself, so skin depth doesn't play a role. And now if we increase the frequency, even if 1 kilohertz, it's still pretty much homogeneous, as you can see. But if we go up to 100 kilohertz, we can clearly see this is now the effect of the skin depth, that the current inside the wire is flowing only on the outer sections. So this is the current. So obviously this is the effect of the skin depth. But what does the skin depth mean actually for the power transfer? And this is something where we need to take a look first at the separated field. So obviously if we go to the magnetic field, it behaves, the way it penetrates into the conductor. In the center of the conductor is a kind of singularity, so there will be no magnetic field. But if we go up higher and now go back to the 100 kilohertz, you can see also this the effect of the skin depth, where the magnetic field is only on the outside. But what about the electric field? Because that's now the main point. If we want to calculate the power flow, we have to multiply the electric with the magnetic field. So the magnetic field penetrates well into the conductor, but the electric field will not. So this is the electric field now at 1 hertz. You can see that it's not penetrating into the conductor. Obviously, if you have the fields penetrating, the high conductivity of the wire will lead to a very low impedance. That means that the field penetrating is mainly governed by the magnetic field. So you see the magnetic field inside the conductor, but you don't see much of the electric field. This changes a little bit when we go higher to the frequency. I mean, it does not change. What's happening? I mean, right now we see the electric field pointing towards the conductor, from the one conductor side to the other conductor side. But if we crank up now a lot here and go back, let's first go back to the electric field at 1 hertz. If I crank up, obviously people have the right feeling. They say, I cannot believe that like the field is zero and it is completely outside. This is true. There will always be an electric field inside the conductor. Only in a perfect electric conductor there will be not one. But this conductor I defined here has a high conductivity of copper, but it's not perfect. So there will be a field, right? And this is how the field looks like. So you can see inside the wire, the electric field is much smaller. Obviously, if I measure the fields at the core, so you see on the outside it's 500 volt per meters, on the inside it's 0.02 volt per meter, so it's like 4 or 5 magnitudes difference in them. But what's now important is that the electric field inside the conductor points in a completely different direction than outside of the conductor. So you see the electric field points in the direction of the longitudinal direction of the wire. So this is obviously a very different direction than it is on the outside. And where's this field coming from? This is actually what you would call the voltage drop along a conductor due to the finite conductivity. So this is the electric field basically pointing from the source to the wire, and which will result in the resistance of the wire. And that means now if we go away from the fields and we go to the power flow, now looking at the power, so here on the outside you can see the power which travels. So this is the Poynting vector. This is the power traveling from the source to the load. But we can also crank up here a lot. And what do we see? That the power flow inside the conductor looks quite strange, right? It's pointing inwards. But this is exactly skin depth. And we can see if we go up, I mean, this is the skin effect. If we go up to 100 kilohertz, you see also that the power is still pointing inwards, and now it's limited to the surrounding, because this is what the fields do here. This is exactly the mechanism of loss inside the conductor that you can see here. Basically, the fields coming from the outside will penetrate into the conductor. This is the skin effect, but the resulting power flow from this penetration will be pointing inwards. It will not transfer energy from the source to the load. It will contribute basically to the loss mechanism. So this is, even if the fields really penetrate into the conductor, they really do not contribute to the power flow from the source to load. They are just inside the conductor and lead basically to losses, which you can see if you look at the power loss density, which also follows like the idea of the skin depth. So at 100 at 1 hertz it's very homogeneous, while at 100 kilohertz the loss is distributed on the outer. So I think it's really safe to say that the energy traveling from the source to load is really inside the space, and even if the fields penetrate into the conductor, they have a very different direction and only lead to the loss mechanism. So skin depth actually does not play a role in the energy transfer, it just plays a role in how the loss will be distributed inside the conductor. So I hope I could, shed some light on this topic. Like this kind of discussions very much because it's very simple and everybody knows about the mechanism, but looking like into the simulation, looking at the details of the fields helps really to understand the very fine details of electromagnetic theory. So hope you enjoyed. Thank you very much for watching and have a nice day.